Okay, we are now recording. All right, so I have prepared PowerPoint presentation to share with you. You see it?
Yep.
Okay, very good. So it's about chapter 22 today, electromagnetic waves. And Kelly, please read the chats for me, if you will, again.
Yes, I will. Thank you.
I think one just appeared, actually.
It was me responding to Julia. Sorry.
Oh, okay, gotcha. All right. All right, so electromagnetic waves. We've been talking about electric fields and magnetic fields and electric phenomena, magnetic phenomena. Well, they come together in this chapter. And the person who brought it all together is James Clerk Maxwell. And there he is, with a glorious beard, as you can see.
He is quite.
So he demands to be in the pantheon, or it doesn't demand, he deserves to be in the pantheon with Newton and Einstein. He's right up there. He really took everything that was known about electricity and magnetism and unified it and put it in a nice, beautiful mathematical framework. So he formulated Maxwell's equations, which are 4 equations, at least the way we write them now, the way he wrote them, that describe all electric and magnetic phenomena classically. So things change a little bit when we get to quantum mechanics in the 20th century. But these equations are still extremely useful and a beautiful synthesis of what everything was known about, what everything that was known about these things. Not the least of his contributions are development and application of vector calculus to put all this stuff together. Just mathematically, the way things were expressed was a complete mess. And he had the mental capacity to draw it all in and see the simplest kind of structure for it. All right, so what do Maxwell's equations tell us? There are 4 of them, as I said. One of them is Gauss's law, which you have discussed, I'm sure. It's a generalization of Coulomb's law, so Coulomb's law is included in that. Another equation is the statement that there are no magnetic monopoles. Consequence of which is that magnetic field lines always form closed loops. So that's the statement about, let me get my pointer here. That's the statement that there are no magnetic monopoles, and then Gauss's law is kind of a statement that there are electric monopoles, and what are the consequences of them. Then there's an equation which tells us Faraday's and Lenz's laws, that a changing magnetic field produces an electric field. And another, by the way, another important piece of this is Faraday's contribution of inventing the idea of fields. So Maxwell's equations are written in terms of the electric and magnetic fields. And then finally, there's another equation which says an electric current produces a magnetic field, which we already know. So Maxwell took all this, put it together, noticed its mathematical consistency, and was able to see through the forest for the trees, as it were. And he noticed that there was a certain symmetry that wasn't quite there. So he imagined that perhaps a changing electric field also produces a magnetic field. It's a new idea. And it makes sense, as I'm going to review in a couple slides here. And so in so doing, he put together everything into Maxwell's equations and immediately saw that there were very interesting consequences to these equations. But that's not all he did, by the way. He contributed immensely to kinetic theory and thermodynamics, which some of us saw at the end of last semester. So he is a giant in the world of physics, right up there with the greats. Now, to talk about this last bit here, let's briefly recall Gauss's and Ampere's law. I don't know to what extent you discussed Gauss's law, but the idea is that you can take a closed surface, like a sphere or a spherical blob thing. This is supposed to be a shaded rendering of a 3-dimensional closed surface of some sort, where there's an electric field. So you see the electric field lines, and you see these thicker lines of the actual electric field at the surface. So you can, in principle, calculate the electric flux through that closed surface. You break up the surface into little tiny areas, delta A1, for example. Find the electric field at that area, find the component of it that's perpendicular to the area, multiply them together. That gives you the flux, the electric flux through that little area, and then do the same thing for all the other areas and add them all up. That's the general idea of calculus, is you break things up into little things and then add them up. So you can calculate what this flux is, and Gauss's law tells us that that flux equals the amount of charge that's enclosed divided by this number epsilon 0. This, I think it's permittivity of free space. Okay, so this is a mathematical property of fields. First of all, so the mathematical property tells you that you can relate, this flux calculation on the surface to a different kind of a vector calculation on the inside, over the volume that's enclosed. And then the physics part of it is that that volume calculation gives you the amount of charge inside that volume. Okay, so that's Gauss's law. That's the first one, and this includes, since it tells you about the electric field, it includes Coulomb's law. Then there's Ampere's law, which I didn't have too much time to discuss, 2 times ago when it was relevant. But let's mention it here. So it's kind of a similar sort of calculation. This is the statement of it. What you do now is you imagine, there's in this case, there are these 2 wires, the 1 wire or 2 wires or 3 or however many. And then there's this plane that's drawn. On the plane, a certain path is mapped out. Whatever that path was, it was broken up into little steps like this. And then what you do to look at Ampere's law here is on the left is a similar calculation to what we did for Gauss's law, except kind of 1 dimension less, if you will. What you do is you take these little tiny steps, these delta L distances, they're little vectors, find the component of the magnetic field that's parallel to those, multiply them together, and then add it up over the whole thing. So that's this kind of, it's not really magnetic flux, but it's kind of a similar calculation to what we did before, in 1 dimension less. And then, as I said, there's a mathematical relationship that is just the nature of vector fields, which relates that to another vector calculation over the area of the surface, which is bounded by that curve. The physics part is that calculation over that area gives you the amount of current that goes through that surface. Okay, so that's a statement of Ampere's law. It works for any kind of a surface, any kind of a curve like this, and whatever surface, that is the edge to. A very useful and simple application of this is to imagine a circle around a single wire. So then the calculation on the left is easy because we know the magnetic field is perpendicular to the circle everywhere. So this calculation just becomes, you can pull the B out of it because B is parallel to all these steps. This becomes the sum of all the steps. The sum of all the steps is the circumference of the circle, so 2 pi r. And so now we can solve for the magnetic field, and we have this equation then for the strength of the magnetic field, the distance r away from the current carrying wire. So this we've used already, and this is basically where it comes from. Everybody with me?
Yes.
I know you are. All right, I want to hear the dings from the chat.
Julia says, how interesting. And Alex says,
Cool.
yes, we're all here. Yep.
Even after a whole semester of doing this, and even after teaching an asynchronous class, when I had to record these things, it's hard to get over the idea that I'm just in a room talking to a laptop.
Yeah, the other end of it is not really any better.
I was not cut out for TV or radio, I guess. Okay, so again, this vector calculation, which gives us Ampere's law, depends on a closed curve and then a surface which is bounded by that closed curve. In this case, what's drawn here is a flat surface with a curve on it. And then we do the calculation over this orange part of the flat surface. It doesn't have to be flat. It doesn't have to be a flat plane. So we have this picture from this chapter. So in this case, what we have is this, this situation, but we take the wire and we rotate it so it's horizontal. And then look at this circle here. See this circle on the flat plane? That's this circle. And applying Ampere's law to surface 1 is what we just did, basically. But as I said, the vector math part of it tells us that it doesn't have to be this surface. You could use this surface. This is kind of like, you can imagine a plastic grocery bag that's inflated. Wind is blowing into it, and it's like that. So the edge of it is here. It's the same edge as surface 1 that we had before. And this is the rest of the bag that's been inflated and blowing in the wind. So you can equally well apply Ampere's law to surface 2 instead of surface 1, and we better get the same answer. Ampere's law tells us this result using surface 1, and it should work for either surface. It's not exactly easy to calculate, but the left side of Ampere's equation, Ampere's law over surface 2, but it should work if you were able to do it. So let's now consider a discharging parallel plate capacitor, which is like this. And here's that same set of surfaces. We have that closed path, surface 1, which we already considered, and then surface 2, which is like the inflated grocery bag.
Looks like a lampshade.
Okay, a lampshade, except that it's in, well, yeah, a lampshade is also in 3 dimensions, isn't it? All right, let's call it a lampshade, except that it's closed on the bottom.
Okay.
The lampshade part of it is open on this end of it, but closed on the bottom. Which, such things exist, diffusers on studio lights. But the key here is that surface 2 doesn't go through the wire, right? So it's open on this end, and then it goes through the space in between the capacitor and then back. So if we apply Ampere's law, surface 2 to surface 2, it should give the same result as applying it to surface 1, and we already know what that answer is. The problem is that if you look at surface 2, no current actually goes through it. Right? Surface 1 is pierced by the wire, and so current goes through it, but no actual current goes through surface 2. So how do we get the same result? Well, the implication is then that this changing electric field and somehow will behave like a current and thus generate a magnetic field, the same magnetic field that we expect if we calculate the surface 1. Remember that if there's a, go ahead, Kelly.
Sorry, I have a question. So basically what it's saying is that the magnetic field that's generated will then essentially surround the lampshade or go around that surface 2, even though it's not.
Yeah.
Okay.
We know what it's going to be like because we know the solution for this wire already, given surface number 1. Right? There's that right-hand rule thing, and it wraps around, and the distance away from the wire goes right. Like the strength of the field is 1 over r. We had that formula a couple slides ago. But we should get the same answer with surface 2.
Okay.
Except that surface 2 doesn't, has no current going through it.
Right. Okay.
Remember that when there is a current in the wire, right, then the capacitor is in this case is discharging, right, because this is positive, so the current's flowing away, and so the amount of charge here is decreasing, and some negative charges, some positive charges accumulating on the other side, which was already negative. So the strength of this magnetic field in this case, the way it's drawn, is decreasing. If there's no current, you can have a charge on the capacitor, but then there's no magnetic field because the current isn't flowing, right? So this happens. This whole argument applies when the current is flowing and the current is flowing and the electric field is changing because the charge on the capacitor is changing. Okay, so what do we know about capacitors? We know Q equals CV. We know for parallel plate capacitors this equation. Let me turn this off. Get rid of that noise. Okay, so we know Q equals CV. We know for a parallel plate capacitor, this expression for the capacitance in terms of the area of the plates and the separation. And the voltage across the capacitor is the electric field times D. So electric field is uniform in there. So electric field times D is the voltage. So we can combine these things, plug the lower two equations into the top one, and we get this. Notice that the D's cancel. And now notice that A times E is the flux, the electric flux, right? You could take this surface and you can imagine that it's sort of tightly fitting around this plate. So the electric field only goes through the portion of surface 2 that corresponds to that same area. So A times E is then the electric flux through surface 2. Okay, so the charge is related to the flux this way, and now since we know there's a current, we know that the charge is changing. The amount of charge is changing. So how much changes in a certain amount of time? We could write this ratio. Epsilon 0 is a constant, so on the other side we have the same sort of formulation, the amount of change in the electric flux over that time period. Well, the rate of change of the charge is the current. So now we have a relationship between the current and the rate of change of the flux, the electric flux. So it implies, this equation then implies that the changing electric flux effectively behaves like a current. Like this current multiplied by epsilon 0, and you get what the current would be. So Maxwell looked at this and he noticed that this changing electric flux behaves as if it were a current. He called it the displacement current that occurs in this space over here. So sometimes you see this equation with a subscript D here for displacement. But it's the same value of the current that's here. So that's pretty cool, right?
Yes.
We have established that as the electric field changes, it behaves like a current, and that's why we have a magnetic field. This makes it consistent with the argument for Ampere's law applied to surface norm of 1. Was there a comment?
No, I was just agreeing with you.
Oh, that it's cool? Yeah, it's cool. Thus, it creates a magnetic field. Changing electric field creates a magnetic field. Okay, so that's the added piece that Maxwell stuck into what was already known, and everything fell into place. And since he was pretty good at math, he noticed some immediate implications to the equations that he wrote down. By the way, you can get a T-shirt with these equations. I don't have one. One of these days, I keep telling myself I'm going to get one. Not sure when I would wear it. But here are Maxwell's equations in this. What was that?
Wear it to every lecture.
Yeah. So this then Maxwell said, and these equations, and there was light. You can also get the version that said, and God said, and then Maxwell's equations, and there was light. So these are Maxwell's equations written in vector calculus form. The first one is Gauss's law. The second one tells us there are no magnetic monopoles. The third one is Ampere's law. So there's the portion that Ampere knew about. The current creates a magnetic field. This is the part that we just talked about where the changing electric flux occurs. And the last one is Faraday and Lenz's law. So as I said, not the least of his contributions are being able to write them in this nice compact form so that they could be interpreted. Before applying vector calculus, you would have 12 big, ugly, really hard to understand equations because they fill up the whole page. Okay, so the implications that Maxwell immediately saw is that we get waves out of these equations. They predict the presence of electromagnetic waves. I shouldn't say presence, I should say existence. And out of that comes the hypothesis that light itself is an electromagnetic wave, as we'll see as we go along. So this led to all kinds of amazing technologies. Once we understood how electric fields, magnetic fields worked, all kinds of things came about. Wireless communication, not the least of it, etc. Okay, so let's discuss a simple antenna for the creation of electromagnetic waves. So here's a wire that's got a current going through it, and then here's an alternating current source. But at this particular moment, the snapshot that's taken here, the current's going up here and then goes through, and it's also going up there. So this upper part gets positively charged, the lower part is negatively charged. And as this current was increasing, this electric field was created, and this magnetic field is created because you see the current is going through the wire. Think about the right-hand rule. If you grab the wire, your fingers on the right of the wire go into the screen. So blue here is indicating the direction of the magnetic field. And then these fields then move outward, right? A certain distance away, as soon as this current flows a certain distance away, there's no electromagnetic field. It has to actually get there. It doesn't occur instantaneously. So it builds up and moves out. But what happens if then this current flips before these electromagnetic fields get very far? So if they flip quickly, you get something like this. The electric fields go back and reconnect, as you can see here, which makes sense because there are no charges out here. Remember, electric fields begin and end on charges, and if there are no charges, then they can have loops. And the magnetic field are always forming loops, always form loops. And so here you can see the loop is going in, the magnetic field, going in on this end and coming out of the screen over here. Right, so that's what happens when the current is going down. Right, use your right-hand rule and grab the wire with your thumb pointing down, and you'll see that if you wrap your fingers around, it will come out of the screen, showing you the magnetic field on this side points out. So you can see that if this current oscillates back and forth, you get these sort of bubbles coming out and then radiating outward. So it has a complicated shape near an antenna, but farther away, they kind of flatten out, and then you get something like this. So this is a plane wave. You can see that's sort of a portion of this wave here. So they're called plane waves. And so that's a much easier structure to understand. So what happens if you're standing over here and this wave washes over you? So the first thing is that you notice that there's a magnetic field, in this case pointing in, and an electric field pointing down. Then as the wave passes by you, those die off, and then you get nothing when this portion of it gets to where you are. And then they start to grow in the opposite directions, the electric field upwards and the magnetic field outward, when this portion of it gets to where you are over here. And then the whole thing repeats as it goes along. Another way to show you the same thing is this. So this is showing sort of the extent of the electromagnetic wave. And notice we have a little Cartesian coordinate system here to show you the depth perception here, x, y, and z. In this case, the electric field is oscillating in the y direction only, and the magnetic field is oscillating in the z direction only. So everywhere along the way, they're perpendicular to each other. So if you're standing here, as I said, the first thing that happens as this wave, this whole structure moves to the right. If you're standing here and it collides with you, the first thing you see is that electric field grows in the downward direction, and simultaneously the magnetic field grows in the sort of, you're facing that way in the rightward direction. Right? And so this whole thing moves to the right, and so then this part gets to you where it's maximal, and they start to die away, and then they flip directions, and then they die away, and they flip directions, etc. But everywhere along the way, the electric field and magnetic field are perpendicular to each other. We won't need this, and the book doesn't talk about it, but it's a nice little story. There's another right-hand rule that tells you the direction in which the magnetic field goes. And that is, if you align your fingers with the electric field and rotate them towards the magnetic field, it tells you the direction of motion of the wave. It's another one of these vector relationships. So there's actually a vector that corresponds to the direction in which the electromagnetic wave goes. It is called the Poynting vector. Not because it points in the direction that the wave goes, but because it was developed by a guy named Poynting, Poyntting. I personally find that really amusing. Okay, I'm a geek. But anyway, Maxwell's equations predict the speed of these waves, not only that they exist, but also give the speed. And he got this answer. The speed of the wave, c, it's a special number. We know it's the speed of light already, so let's just call it c. The speed of these waves is this, 1 over the square root of epsilon 0 mu 0. And remember that epsilon 0 mu 0 are constants. They're fundamental constants of nature. I forget what they're called. One is the permittivity of free space, and the other is, I think, the permeability. But whatever, they're certain numbers. And you can plug them in and you get a specific answer. 3 times 10 to the 8 meters per second. They're rounded. It's 2.99 something or other. But you get a specific number. And that's, I think at the time, there were good measurements, approximately good measurements of the speed of light. So I don't think it was lost on Maxwell that the number that popped out was the speed of light. But this result, in addition to being really exciting and interesting, was mysterious for 2 specific reasons. Number one, what is the medium in which electromagnetic waves happen? Think about water waves. Water waves happen, well, in water. If you don't have any water, you don't have any water waves. Sound waves happen in air. If you don't have any air, you don't have any sound. So what is the medium for electromagnetic waves? That was a big mystery because every wave that was known up until then had a medium. And so people started talking about, well, this means that there must exist a certain substance in nature, and they gave it a name. They called it the luminiferous ether. And a lot of people tried for a very long time to measure it, to observe the luminiferous ether. They all failed, by the way. The other mystery is, what is the speed that popped out of the equations? What is it relative to? So suppose you have some equations and you're able to calculate the speed of a boat in a river. And you get, I don't know, whatever, 20 miles per hour. You're left with the question, 20 miles per hour relative to what? Is that relative to the speed of the water? Is that relative to somebody standing on the riverbank? Is that relative to somebody in a different boat going at some other speed? But people couldn't answer this question. What is the speed relative? The equations were unambiguous. There is a speed, and this is what it is. What's it relative to? So, big mystery. Many years later, Einstein imagines that the answer to the first one is that there is no medium, so there's no medium. And the answer to the second one is that the speed was relative to everything. The mind-blowing idea that anybody who measures the speed of light gets the same answer. So on the basis of these 2 kind of weird ideas comes the theory of relativity in 1905. But I'm getting way ahead of myself, so I've got to go back. Let's go back to Mr. Heinrich Hertz. So he was the guy who was first able to generate and detect electromagnetic waves. He did this in 1887. Unfortunately, some years after Maxwell died. So Maxwell wasn't able to live to see the experimental demonstration of these electromagnetic waves. But he did. This is Hertz, by the way. He of the units, 1 over seconds, is named after this guy. And I got to say, every time I see this picture, I think of the horrible comb over that my future might have if I'm not careful.
I think that
anyway,
people shave their heads now. So
yeah, I might go that way, or just wear a hat all the time. Anyway, not only that, he was able to show that the electromagnetic waves had the same characteristics of light. They reflect, they refract, they interfere. And we'll be talking more about that in the next couple of chapters. So pretty cool. And of course, out of this comes, radio, Marconi, and all of that. And then later on, AM radio, FM radio, television, etc. Okay, some comments about the electromagnetic spectrum. Well, light is a wave, and so this relationship that the speed of the wave equals the wavelength times the frequency applies. This applies to any wave, and so it applies in particular to electromagnetic waves. And so there's a whole spectrum of different kinds of waves, electromagnetic waves. And they have these names: radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays. And here they are laid out with their wavelengths and frequencies. Radio waves are here, AM radio, FM, etc. Cellular phones over here. Microwaves, even the microwaves in your oven are in. They're about centimeters or so, so that would put them, let's see where. This is meters, so I don't know, somewhere over here. And then visible light. On the other side, ultraviolet light, X-rays that you get at your dentist's office, gamma rays. Okay, so there's a comment on absorption. So an interesting question is, why is it that this little tiny sliver of the entire electromagnetic spectrum is what we can see? We can't see these other things. We can feel infrared because it warms us up. But we can't see any of these other things. We don't see radio waves, you don't see gamma rays, you don't see X-rays. Why can we only see this tiny little sliver? Well, if you examine the properties of water, H2O, water, which I need some. Excuse me. If you examine the properties of water and their ability to absorb electromagnetic radiation, you will see that water is pretty good at absorbing electromagnetic radiation, except in these particular frequencies here and wavelengths. So the graph looks like this. It goes very good at absorbing, very good at absorbing, terrible at absorbing, terrible at absorbing, and then really good at absorbing, really good at absorbing. So that seems to imply that evolution selected for us to be able to see visible light because a lot of evolution happened in water. Well, imagine a fish underwater, not terribly far underwater, so that there's some light. If it has eyes that are sensible, that are able to sense wavelengths that can actually propagate in water, then that would be useful information for being able to survive. There's no point in being able to observe, say, X-rays because they don't get anywhere in water. They just get absorbed. Now, isn't that cool? You got to admit that's really cool, right?
Indeed.
That's why we see visible light. I'm sure that you're all oohing and eyeing out there, even though I can't hear any or see any of you.
I'm imagining all of the fish in the very, very bottom where they have like the ghostly, creepy features and,
Yeah.
Anyway, move on.
Yeah, and lots of different things have different absorptions of electromagnetic waves. For example, glass. Glass is pretty good at absorbing ultraviolet. So you don't get sunburn, too much of a sunburn if there's glass between you and the sun. The sunblock, for that matter, sunblock is good at blocking ultraviolet. It's designed to be that way. There are cameras which can be made to be sensitive to ultraviolet light, and you can make a movie of somebody putting on sunblock, and it looks like somebody takes this black paste and just smears it all over themselves, which is exactly what's going on, right? You're putting on something which blocks the ultraviolet light.
It's also interesting that some animals, like bees, see waves in addition to visible light.
Yeah, exactly. So how did that come about? I don't have the answer to that. But yeah, there's no reason why evolution would draw these hard boundaries here. If there's a benefit to these other frequencies, then why not? Okay. At this point, let's do a problem. So I looked at the, was there a comment?
I just said biodiversity strikes again.
Yeah. I looked at the homework for this chapter, and it's really simple. Basically, it's just this equation. Use this equation, except for the last problem, for which you need to know something about intensity falling off as 1 over r squared, which I'll mention. So I asked Dr. Kroon, what should I do? And he gave me a list of problems, and so I'm going to solve some of those problems for you. I don't have time to do them all. Here's one of them. And this goes back to the idea of the capacitor changing with the electric field in between. So determine the rate at which the electric field changes between the round plates of the capacitor that are 8 centimeters in diameter, if the plates are separated by 1.1 millimeters, and the voltage across the capacitor changes at a rate of 120 volts per second. This is problem 1 from the end of the chapter problems. So here's the picture. The current is going in. The electric field is changing at a rate of 120 volts per second. Here are the dimensions. We want to know what the rate at which the electric field, we're given what the voltage changes is, volts per second. We want to know what the electric field rate of change is. Okay, so here's this relationship that relates the voltage to the electric field. So a change in voltage equals this change in electric field, and D is a constant, so there's no change in the D. Divide by the time interval over which that change occurred, and solve for what we want, the rate of change of the electric field. That's it. Then plug in the numbers. So for the separation, we have 1.1 millimeters. I wrote that this way in terms of meters. The units are consistent. The rate of change of the voltage is given, 120 volts per second. So we get this answer. The rate of change of the electric field is this number, volts per meter second. Maybe I should say volts per meter per second. Remember that a volt per meter is the same as a Newton per Coulomb, if you prefer to think of electric field in newtons per Coulomb. Okay, so it's a straightforward problem. Just basically use this formula and plug in the numbers. But here's a similar problem, number 2. Calculate the displacement current between the square plates. In other words, we know there's a changing electric field here because the current is flowing. What's the effective current in terms of creating a magnetic field? That's what the displacement current is. So what is it between these square plates? Here are some dimensions that are given, and they tell us that the electric field changes at this rate, 1.6 million volts per meter per second. So here's the formula for that displacement current. Before I didn't have the D subscript, so I put it in here because that's what it is, the displacement current. What is the flux? Well, the flux is the area times the area of these plates, which you can't see because they're end on, right? So the area times electric field. And so the rate of change, the amount of change that occurs when the flux changes is equal to the amount of change of the E. A doesn't change, divided by the time interval. Then we can plug that into the equation above, just multiply it by the epsilon 0, and that gives us the displacement current. Plug in the numbers. There's the epsilon 0. Here's the given value for rate of change of the electric field. Separation, rather the area, written in square meters, gives us this many amps. Okay, so again, it's just basically apply this formula. And in order to apply the formula, you need to know what it means. And so hopefully these problems help you sort out what the meaning of these formulas are. Now you might be wondering, how in the world did we go from this to amps? So what are the units? That's the formula that we had, and my claim was that it gave us a certain number of amps. How do we go from these units to amps? Look how ugly that is. So here I picked out the units just by themselves, so I have an arrow indicating that. You can see that the meters squared cancel out. You can do that immediately. So we're left with this. Now let's break up these Coulomb squareds and do a Coulomb times a Coulomb and rearrange a little bit. So we have this. Right, so here the Coulomb squared is Coulomb times Coulomb, and I move the seconds over to this side. And then put parentheses around things. A Coulomb per second, well, that's an amp. And here in the denominator, a Newton meter. Everybody remember what that is? That's right, it's a joule. So we have amps, in parentheses, Coulomb per joule, and then volts. Do you remember what a volt is? A volt is a joule per Coulomb. So you see that these will cancel each other, and you're just left with the amps. So that's how these units work out. I warned you at the end of last semester that the units would get more complicated.
You know, I was just thinking that.
And we haven't said anything about inductance and Henrys and things like that.
Oh,
So yeah, they all work out, but it's just more complicated, more things to manipulate. Yay. Okay, a couple words on energy in electric and magnetic fields. This section of the book gets really complicated. I don't know how Dr. Kroon presented it or will present it if he hasn't yet. But it gets complicated not because it's hard, but because there's just a lot of equations. So hopefully what I say will help you sort it out. Here is the energy density stored in an electric field. Its units are joules per cubic meter. So wherever there's an electric field, there's energy in that field. And this is the number of joules per cubic meter of energy that are there. You can write a similar equation for the magnetic field, except that the number here is in the denominator, the mu zero. And so when you have an electromagnetic field, remember that the magnitudes of E and B, they changed at the same rate so that they're both zero at the same time and both maximum at the same time. So the energy density stored in a region of space where there is an electromagnetic wave, so you have electric and magnetic fields, is the sum of these two things. And that tells you the number of joules per cubic meter. So all of that is true for fixed or instantaneous values of electric field and magnetic fields. So with this, we can answer the question, before I get to that, take that formula that we just wrote down, energy density where there's electric and magnetic fields, combine it with this result from Maxwell's equation for the speed of light, the speed of the electromagnetic wave. I didn't tell you this part of it before, but yeah, that speed could be written as E divided by B. Just take these are three equations, I guess. If you combine them, you can get a whole bunch of different formulas, and that's what they do on page 633 in the book. That's the part that's really kind of messy. Lots of different ways of expressing different things just by mixing these things. Similar to what we did with like power. Remember power and Ohm's law? You can combine them and you get different forms of the power.
so is that just for essentially if they're asking a different component, you'd want to know a different variation of all three of them?
Yes, solve for one thing in terms of another.
Okay.
You just get lots of different relationships. But we have a question which this formula here allows us to answer now. That is, how much energy is delivered by an electromagnetic wave as it propagates? So how would you even answer that question? You would have to say how many joules arrive in a certain area per unit time. Well, that's intensity. You might remember that from sound. Intensity is the energy that arrives at a certain area per unit of time. And that's measured in joules per second per meter squared, or watts per second. Well, here's the picture of the electromagnetic wave, and it's propagating to the right. And this gray area is a volume where the electromagnetic field is, and the thickness of it is how far the wave traveled in a certain amount of time, delta t. Okay, so you're standing there, and then the wave travels over a certain amount of time, delta t, and it swept through this volume. Since we know the density of energy, we can figure out how much energy is in that volume. It's this density of energy times that volume. We can write the volume as the cross-sectional area A times this thickness x, or rather delta x, and that delta x can be related to the speed of the wave because it's just c times delta t. Distance is velocity times time. So the energy in that gray box is UAC times delta t. Well, what we wanted to know was the energy delivered per unit of area per unit second, per second, which would be E divided by A delta t. There's the E, there's the A, there's the delta t. So I just move those over to the other side. I have my answer, U times C. So the intensity of an electromagnetic wave is this energy density times the speed of the wave. Now, one last thing to tell you about these things. Remember this from sound. For three-dimensional waves, the intensity, which, as I've been describing, is a certain amount of energy over a spherical shell. It's at any given time, let's take a snapshot in time, the spherical shell has a certain amount of energy on it. And as time goes on, you don't lose or gain any more energy. It just gets spread out over more and more area. So the area is 4 pi r squared, right? So put these two ideas together. Since you have the area in the denominator of the intensity, you can conclude that the intensity goes like 1 over r squared. Intensity decreases the farther out the wave propagates, because it propagates in 3 dimensions like this, right? That energy gets distributed over more and more area, and so it thins out, if you will. So intensity decreases like that. Okay, so you have these 4 equations, and again, you can combine them in many, many different ways to get expressions like this for the intensity. Oh, I'm almost out of time, I see. All right, so I'm going to pause here, get a screenshot of the attendance before I forget. Nobody go away yet. Come on yourselves. Hold on. Okay, I have the attendance. Is Mark Mata here? He's actually not here today. Okay. All right. What was Blackboard recently added my middle name? Okay. Let me have just a moment to finish the ideas of the slide. So, what I was telling you is that we have this equation for the energy density where there's electromagnetic fields, these expressions for the speed of the magnetic field, and this relationship for the intensity. You can combine them to get things like this. And notice this first one, we can do something with that first one. This intensity is this. So, as you're standing here, the electric field grows and shrinks and grows and shrinks, so the intensity grows and shrinks and grows and shrinks. So it's kind of reasonable to talk about an average intensity. You can write an average intensity. Here, these angle brackets are time averages. And remember that, and the root mean square of something is the square root of the average of the square, as it's written here. So you can solve that for this and express the average intensity in terms of the RMS values of E. And there are similar equations for B. So I mention that because there are some problems, which I will not do now, but I will have written out for you in the slides here. I'll post them, you can have a look at them. And that's what I had for you. A couple more slides, but not something urgent. I'm out of time. I hope this was helpful and useful. Was it helpful? Useful to do this?
Very.
Okay. I'll post this. I'll have an office hour tomorrow. I'll post the hour in the Zoom link. Have a look for that. I don't have separate written out problems this time because I incorporated them into the presentation. But have a good weekend, everyone.
Thank you. You too.
Hey, guys. I'll stick around for another 5 minutes or so if you have questions.
Dr.
Bye. Yeah.
What does the U stand for in the I equals UC equation again?
Energy density. It's how many joules are in, how much energy is there in the space where the magnetic and electric fields are? How many joules per cubic meter of space?
Thank you.
Right,
And then,
due to the electric and magnetic fields.
And then those angle brackets, you said those mean average?
Time average in particular, yeah.
Time average. Okay, thank you.
Mm-hmm.
I guess you won't be having office hours this week since we had the exam this past week.
Yeah, I'll do it tomorrow.
Oh, all right, wonderful. Thank you, Dr. Brado.
I'll post the hour and the Zoom link in the announcements section.
Okay.
Of Blackboard.
And if we're unable to make it for some reason, you'll be able to record it as well.
Yeah, I'll record it, sure.
Wonderful. Thank you, Dr. Brado.
Which reminds me to turn off the recording.
Okay.
Okay.
All right. Thank you.
See you, everybody.
Everyone.
Stop recording. Bye.